Hello and welcome to part one of our virtual class. Please excuse the room lights on my glasses and the horrible coordination of video and audio, but it's either this or risking driving home in the snow tonight. Now, we left off with the drinking water exposure limit, or the amount of a substance that it is safe to consume through the route of exposure of drinking water. Now remember that there are several different types of routes of exposure. When we're talking about chemicals, we can drink them or eat them in our food. We can breathe them in through our lungs. We can absorb them through our skin, or we can have contact with our skin. But let's look at this route of exposure through drinking water. So we're going to begin by laying out some assumptions. We'll assume that the average person weighs 70 kilograms, and we will assume that the average person drinks 2 liters of water per day, and that 20% of a person's exposure to that chemical will come from drinking water. Now, wait a minute. What do we mean by that? Well, we could be exposed to a chemical in any number of ways. We can have skin contact. We could have absorption through the skin. We can breathe it in and have the route of exposure through our nasal passages and lungs. But that would be 100% of the exposure. In this instance, we are assuming that only 20% of our exposure to this material comes from our drinking water. Now let's go back to slide 43 for a moment and look at a dose and uncertainty that's going to give us an acceptable daily intake. So if we have a lowest observed adverse effects level of 1 milligram per kilogram of body weight, and we have an uncertainty factor of 100, we get 0.01 milligram of this chemical, xamphelamine hydrochloride, per kilogram of body weight. So now let's see what we can do with these numbers. So to set a drinking water exposure limit, we take our reference dose, we multiply it by the body weight, and we divide it by the amount of water a person is likely to drink. Now, we can argue or we can discuss whether 70 kilograms is an appropriate body weight, and we can argue whether we drink 2 liters of water a day or what percentage of that might come from cooking. But these are the numbers that have been worked out by the U.S. Geological Survey for groundwater and the U.S. EPA for general exposure to harmful materials in drinking water. So the generalized formula for the drinking water exposure limit is the reference dose times the body weight divided by the daily water intake. Of course, we can add to that, but this is the minimum that we need to calculate a drinking water exposure level or drinking water exposure limit. So we work out our reference dose as 0.01 milligram per kilogram of body weight times 70 kilograms of body weight divided by 2 liters of water per day. Now, this 1,000 here is a conversion factor to go from units of milligrams per liter to units of micrograms per liter, because there are 1,000 micrograms in every milligram. Now, we could, of course, publish a drinking water exposure limit in units of milligrams per liter or parts per million, but most people prefer to work in units of micrograms per liter or parts per billion. So milligrams per kilogram of body weight per day times 70 kilograms typical body weight times 1,000 to convert from milligrams to micrograms divided by 2 liters of water a day gives us a drinking water exposure limit for xanthamine hydrochloride at 350 micrograms per liter. Okay, so what have we added to our thinking? What have we added to our understanding of the dose-response curve and what we can do with the dose-response curve? Okay, we have a lowest observed adverse effects limit or a no observed adverse effects level. We then add the uncertainty factor to give us our ADI or acceptable daily intake, which we can also call a reference dose. But now we have combined it specifically with body weight and a specific route of exposure, in this case, drinking water, to give us the drinking water exposure limit. So now, what about exposure over the course of a lifetime? We were given a limit of 350 micrograms per liter, but that says absolutely nothing about the time of the exposure. So we take our drinking water exposure limit times the relative source contribution, in this case assumed to be 20%, and divided it by an additional uncertainty factor. That gives us a lifetime health advisory of 7 micrograms per liter. 350 micrograms per liter times only 20% of our exposure to this chemical will come from drinking water. Again, that's an assumption we can make. We can have 100% of our exposure coming from drinking water, or we can have 50% from drinking water and 50% from food, or we can have 20% from drinking water and 80% from skin contact. But the point is that we are accounting for only the amount of this material that comes from drinking water that will set a lifetime health advisory for exposure through drinking water. So, as before, we start with a dose-response curve to give us a lowest observed adverse effects level and a no observed adverse effects level. We divide that by our uncertainty factor to give us our ADI, or acceptable daily intake, which we could also call a reference dose, or in this case, an oral reference dose, since we're talking about exposure through the mouth and drinking. Now we've combined that with the body weight and route of exposure to give us a lifetime health advisory obtained from the percentage of this chemical obtained through a particular route of exposure, drinking water in this case, and of course, an additional uncertainty factor. So why is this important to public health? Now, because YouTube does not allow me to upload long videos, I'm going to pause it here and we'll resume with part 2.